So, hi everyone, I'm Jesus Ligero. I'm from Protocol and Integration team of Polygon-Hermez, and I will present our bridge approach in Polygon zkEVM. So, first of all, the introduction, basically what we want to build is a bridge that it's be able to transfer assets in a reliable way, smart contract secured, and minimize the gas cost and the delay. And also our approach attempts to be able to interconnect multiple rollups using the same bridge, right? This approach is based on this ether research that was made by Vitalik and a discussion from Vitalik and Jordi Bailina. If you want to check it out, I recommend it. It's very interesting. So let's put it on a quick overview. Okay, well, it's a little bit, it's okay. So the idea of the approach is that here we have 4 networks. Do you see mainnet, that it's layer 1, rollup 1, rollup 2, rollup 3. And the idea is that every network will have an exit tree, which will contain the exit information of this network. With this, I mean that every time a user wants to transfer assets from one network to another, the user will, the bridge will add an exit leaf to the exit tree of that network. In the same way, we take all the exit trees of all the networks and we merkleize in what we call the global exit tree route. So the global exit tree route will be the source of communication of the rollups. So for example, in the last example I put, if I want to bridge some assets to the mainnet, from the mainnet to the rollup 1, a new leaf in the exit tree of the layer 1 will be created with more or less that information: origin network mainnet, destination network rollup 1, and then amount and destination address and so on, the meta information, right? And then from the rollup 1, we can check things like we have the global exit route. With a Merkle proof, we can prove that exists this leaf, and therefore we can claim the tokens that came from the layer 1 to the rollup 1. And of course, the other way around will be possible also. Okay, so this slide is more like the other slide. It was more general, and this is more similar. With the current implementation that we have, here we have mainnet, and here we have our zkEVM. As we see, is very similar. If a bridge smart contract is called, a new leaf is added to the exit tree, and therefore the exit tree route is updated, and therefore the global exit tree route is updated. Then the zero knowledge proof or the circuit should be able to make available this global exit tree route that is on mainnet in the zkEVM. So this is what basically will do the circuit and computes all the transactions and so on. So in the zkEVM, we will be able to have the availability of the global exit tree route and therefore claim the assets that came from mainnet. And basically the other way around. When as zkEVM we want to bridge something to the mainnet, we call the same bridge smart contract that will be on the zkEVM. We'll update the exit tree of the zkEVM. The circuit will make sure that this tree will be updated on mainnet, the exit tree route of the zkEVM, and therefore on mainnet we should be able to claim these assets. Now, next we will do a flow of all of this if it's not clear enough, and I think maybe we'll answer your questions. So first, I will do how we implement the logic that I just put, the schema. So I will put the smart contracts that we use to implement this. Basically, we have 3. The bridge will be a smart contract that basically what it does is you can claim assets from another networks or bridge assets to another networks, right? The bridge will update the exit tree, as I said before, that will be updating the global exit tree route. Also, we have the global exit route manager that basically is a contract that just manages the global exit tree route. This, we separate the logic that the bridge with the global exit route manager because in this way we can deploy exactly the same logic of the bridge, exactly the same bytecode in all the networks. So this makes more interoperable, right, and more easy to use. And the global exit route will be different depending on the network. In the next slide, I will explain more about it. You will see it. And lastly, we have the consensus contract that, in our case, will be the proof of efficiency. I don't want to get into details of this. I just put it because it's the consensus contract that we are, and I will just point that out what is important for the bridge, and that's it. Okay. So as we see in the Yes, you can read it. In the batch information, basically, we have one call that it's called sequence batches, where the sequencer are the transactions, and also the global exit tree root is taken from the global exit tree root manager, and this will be an input in the verifier. So as I said before, basically we have some kind of input in the verifier and the circuit that will force to make available in the zkEVM. So in order to in the zkEVM, you will be able to claim the assets that came from the layer 1, right? And now we'll explain the smart contracts in the layer 2, that as you see, the bridge is exactly the same bridge, but the global exit root manager will be different. This will be a very special contract because this contract is updated by the circuit or the zero knowledge proof. The zero knowledge proof will write in some specific storage slot of this contract in order to make it available in the zkEVM. So every time there is a new batch to process, every time we process a batch in the circuit, at the start of all the transactions, we write the global exit tree root in some storage slot of this contract, and then the bridge will be able to call it to claim, as we see here. And also at the end of the batch, we will read the exit tree root of the zkEVM, and we will write it on mainnet, as we said before. And now I will do it is bridge, but it's crooked, you know. But it's bridge technical details. So we'll do a little bit of technical details of how is done the bridge, and then I will do a full flow to finish the presentation. Okay. So the bridge is done basically, as we saw before, it has to compute a Merkle tree. It's a Merkle tree that it's append only, and this logic is already done. It's done by the Ethereum 2.0 deposit contract. So basically, we base our implementation on that because it works. It has a formal verification, and it's pretty efficient. So basically, it's the same Ethereum 2.0 deposit contract, but we change a little things, like the leaf is different, and the base hash in the deposit contract is SHA, and we use kecak because it's cheaper in the Ethereum. So, and it's compatible with our EVM, so we use that. Also, for the bridge will create for sure wrapped tokens every time a new token is added to this network, and the metadata of this token, as the name, the decimals, or the symbol, will be added to the information of the leaf as well. So everything will be secured by the smart contract. Okay, so this is the flow. I will do two flows from mainnet to zkEVM and the other way around. Maybe with this will be all clear. So let's start. Let's have a user that wants to bridge something to the zkEVM. The user will call the bridge information. A new leaf like this will be created, origin network, destination network, as you see. And for example, he's reaching Matic, so the metadata will be Matic token because a new wrapped will be created in the zkEVM. This will be updated the exit tree of layer 1, that also will be update the global exit tree root. So we have the global exit tree root containing this information. The second part will be once a batch is processed in the zkEVM, the circuit will write the mainnet global exit tree root in the zkEVM, so will be available in zkEVM, so in layer 2. And lastly, since this information is available with a Merkle proof, we are able to prove that there is a leaf that came from mainnet, so we are able to claim these tokens. Since this is the first time this token is reached, a new wrapped will be created with the information that we see in the metadata. And for the other way around, we have exactly the same interface for the bridge, you see, but well, this time the destination is mainnet, it's not zkEVM. It's very similar, but just now we are updating the zkEVM root instead of the mainnet because we are on zkEVM. And then we have to wait that a new batch is verified. Once the new batch is verified, the exit tree that the circuit reads will be updated to the mainnet, basically, as we see on this schema. This is layer 2 and this is layer 1, just to make sure that you see it. And well, basically, once the batch is verified, the global exit tree root will be updated with the information of the leaf that we just created, and then we can just claim it with the same Merkle proof. As you see, the schema is very similar, but we have to wait that a batch is verified in order to claim it. Just to finish, I think I go pretty fast. Well, it's okay. There is open issues like bridge NFTs. We have more or less the approach. We have the metadata field in order to bridge the metadata NFTs, but it's not done yet, but we know more or less how to do it. Also, one thing that we are considering is bridge smart contract calls, like arbitrary smart contract calls. This could be done, but it's a little bit more trickier. And in the end, we'll want to optimize the gas, and pretty much that's it. So thank you so much for attending. And so do you have any questions?
Yeah, we have time for a few questions. Wait, one second.
Thanks. So is for logic like NFT, how you say it's starting with just tokens, and if you're going like NFTs in execution, does that mean then basically those are like hard-coded paths that you have to take within the bridge, or is it arbitrary as like a base layer?
The NFTs, you say?
Well, just like the bridge function, for instance, is that like an arbitrary based approach, and then like you're just like encoding it differently at the destination, or do you have to like re-update everything every time you want to like add new functionality?
So this is what I want to like. You see, like on open issues, there's an arbitrary smart contract call. This could be inside this this feature, and we are contemplating. You can do, for example, you want to bridge different types of NFTs. You can do like different types of, I don't know, smart contract calls that calls a contract that creates an NFT with whatever metadata or type of NFT you want. So this will be inside like this group of open issues. Does this resolve your question?
I'll ask you after.
Okay.
And one last one is, can you like withdraw to any other like layer, or do you have to go back to L1 then to like a different one?
Yeah, it's a good question. I didn't explain that. The idea of this approach is like the global exit route contains all the information of all the layers. So if I'm connected 2 or 3 rollups, I can transfer assets from the rollup 1 to the rollup 3, and I don't have to go through my net, so it's cheaper. Thank you.
We have time for one more question.
Thank you for the presentation. I have a tech question about the signatures because we have the verify authority code to verify the signatures. And then I want to know, is the signature saved offline, or is it just saved on the chain and to verify the signature?
Sorry. Can you ask again? The signature of what?
The signature, for example, I want to take the token on the R1. Yeah. So that the signature it is I sign some transaction. The signature is saved in the R1 and then use the verify smart contract to verify signature, or just get the signature directly send the 2 parameters.
I see. So the verifier does not verify a signature; it verifies a zero-knowledge proof of a circuit.
Okay.
So maybe you misunderstand that.
Yeah. Okay.
It may be. Okay. If not, you can ask me later and we can resolve it. But the verifier, it's about the zero-knowledge proof, the circuit. Like it verifies the whole EVM in our case.
Great. Thank you again. Thank you very much.
Thank you very much.